5 का क्वेश्चन
Total 5.
टोटल 5 का क्वेश्चन बस 7 हमारे
What is that? Question. Huh. Total 6, question number 7. So what is the issue? I want you to think about it. I don't want to do this step by step solution. You should think and then ask me. So what is your difficulty? What is the problem? What difficulty you are facing in this question? I have given you the reflected shape of the shear wall. Once you know reflected shape, you can calculate delta D. You can also calculate delta Y. I have given you how to calculate delta Y also. So there is the problem. Up till yield point, the shear wall will be formed till yielding occurs. Shear wall will be formed like a cantilever. How to get the deflection at any height? I have given you the expression. After that, what will happen? When it yields here, it will rotate like a rigid body. Okay. And the additional displacement is simply the plastic rotation into height. The second component in that delta I corresponds to this part. So up to yield point, it is like a cantilever. We have obtained the deflected shape from curvature diagram, and after yielding occurs, it will rotate like a rigid body. So that also I have given. Where is the difficulty? There are issues. That's why I have given question. But until unless you will start thinking, you will not be able to understand that. Not always negative. In this question, the second part is coming out to be negative. Right. Because theta C, you have to calculate theta C. Right. Right. This point 0 is very small. So, if second part, this is the first part. Second part is that it has developed a hinge here, and then it is simply rotating like this as a straight line. This angle is theta p, that is theta c minus epsilon y. What is that?
HN upon L2.
HN over L2. Okay, so this is coming out to be negative. What does that mean? It means that it is not yielding. The design displacement is somewhere here. Here itself, it reaches theta c. So that means it is elastic. So the deflected shape will be given by elastic shape. In elastic shape, you are getting epsilon y, that is at yield. It is less than that. So in place of epsilon y, you will substitute some value of epsilon. You will get, second term you will neglect. You will remove because that is negative. Then you will get the value of epsilon. Because the walls are having different lengths, LW is different. So you will get different strain, although that strain will be less than epsilon y. But it will be different in one wall, different in the other wall. So you can calculate the corresponding value of epsilon 1, and then if you substitute that, you will get the distribution of the displacement along height or the deformed shape along height. Once you know that, and it is not yielding, which is the magnetic last one. So mu is equal to 1, psi is equal to 0.05, no r psi will also be equal to 1, and we solve it. How much is that? No, you got to minus the second term. Minus 0.09 to 0.0218. That means the 2.1%. Okay. So if interstellar drift, you are allowing more than 2%, then you worry. So do it. We will be meeting on Monday and Tuesday also. If you have any problem, we will discuss there. But try. I want you to think. Okay. You should not just remember the formula with the value and do that. You should think when that formula is applicable. If you are getting any unexpected result, what does that mean? You should be able to understand that why you are getting that unexpected result. And if it is unexpected, what should I do? So, can we go forward to chimney? So, chimney is one very common industrial structure, and it is governed, the earthquake resistant design of chimneys is governed by the IS 1893, okay, part 4. That is industrial structures. Again, IS 1894 IS 1893 part 4 also has two parts. The first part is regarding industrial structures, and second part is regarding stack-like structures. So chimney is one of the stack-like structures. Other stack-like structures where you are putting stack means what? You are stacking one section above the other. So any other stack-like structure you know other than chimney? Silo. Okay. So that is also vertical cylinders. Cooling towers. Those are also stack-like. So such structures are governed by the second part of this code, IS 1893 part 4. So you have to go to the second half of this code. There you will find guidelines related to seismic design of chimneys. And the purpose of these chimneys is to discharge industrial gases, okay, at sufficient height into the atmosphere so that concentration at ground surface is within permissible limits. Okay, it gets mixed up with atmospheric air at the height so that the particulates and gases which we are getting at the base, okay, are not too high. There are certain terms which we use in case of chimneys, I just want you to introduce to that. So there is a term we call stack. So the stack is a cluster of several chimneys. Supported by single structure. So many times you will see that the number of chimneys are there, and those are supported by one truss-like structure, okay, tower-like structure, vertically. Then flue, within that stack, the several chimneys, these will called flues. Flue. Okay, so these are separate conduits discharging gases within the same structure. So there can be an independent chimney, there can be a conduit, and that conduit or a set of conduits, and that set of conduits is supported by separate structure. So actual chimney may be flexible, quite flexible, it cannot support itself, but we may provide a separate, generally steel tower-like structure which will support those chimneys. Then we have a term called guide, or guide tower, or guide chimneys. Okay, so this guide is nothing but a wire or rope supporting the chimney. One end is connected to chimney, and the other end anchored into the ground. So we can have a chimney which is supporting itself. It's like a cantilever. Okay. Then we can have a chimney which is supported by these guides. So this is called guide chimney, and this is called self support. What will be the difference during earthquake? This will act like a cantilever, whereas this will act like a drop cantilever. Okay. Behavior of this: due to wind or earthquake, it will act like a cantilever, whereas this will act like drop. Then we have bracketed chimney. Okay, so this bracketed chimney is like the stack which I was talking. So the stack is just representing a set of chimney. Okay, but if you provide a separate structure, so these are the chimneys which are supported by a separate separate doesn't mean that it is away from the chimney, means other than the chimney. So chimney is not self-supporting, but we provide a tower-like structure which is supporting it. Okay. So this is external construction. Okay. So all the loads, especially wind and earthquake, are registered by the external structure. This external structure we call bracket. Then we also have double skin chimney. So you know, chimneys are many times carrying hot gases. The temperature may be very high. Okay, and those gases may also be corrosive. So you require an insulation. Okay, to save the structure from the corrosive effect of the gases and hot temperature gradient. So we provide an inner lining, and the outer shell is resisting the force. Okay, so this consists of two shells. Outer shell supports the chimney against loads, and the inner shell or lining, inner shell which is also called lining, this saves or protects the outer shell from hot corrosive gases. You might have heard about refractory bricks. So what are refractory bricks? Ceramic, some sort of ceramic, the burnt clay. Okay, so the burnt clay becomes, when you burn the clay, chemical changes takes place and it becomes quite resistive to the corrosive effect of different chemicals, and it can also resist large temperatures. and it has good insulation also. So the temperature change in the structure is reduced, temperature gradient in the outer shell is reduced, and also the outer shell is protected from the corrosive gases. Then we have a component called cowl. You can think like bowl. So at the top of chimney, inverted bowl is there. So that is called cowl. What is the purpose? This type of not air. Otherwise gases will not be able to pass here. Okay. So this type of structure is provided at the top, or maybe top or conical, just to prevent rainwater. Try to study chimneys as a separate chapter. Advanced structures or advanced designs. So, what are the issues? Which makes its design different from normal structure. You have learned design of normal structure, you can do. So why not design? Why can't you design chimney also in the same way? Okay. So there are some specific issues. One is temperature gradient. So generally the gases are hot. So inner temperature, the inner surface temperature will be much higher than the outer surface temperature. There will be temperature gradient. Okay. And temperature gradient will cause additional stresses. If it is uniform increase of temperature, then there is not much problem. Its diameter increase, its height increase will not be a problem. But temperature gradient is the problem. Temperature gradient causes moments. Okay. And that causes additional stresses. That is one problem. Secondly, these chimneys are usually tall, so more than earthquake actually, it is wind force, which is a problem for design of chimneys. Actually, these are tall and flexible structures, so period is longer. Earthquake force will be less, in flexible structures. Wind force, on the other hand, is more on flexible structures. And then there is a phenomena of vortex shedding. What is this phenomena of vortex shedding? You might have heard in hydraulics, fluid dynamics class. What is vortex shedding? तो बोलो ठीक है vortex बनता है why? So when you have a circular blunt object, okay, and fluid is flowing, whether it is water or wind, the fluid flows. So here there is a separation around this vortex. There is a separation. So these are the streamlines through which, along which the fluid flow is taking place. Here, in this region, okay, there is instability in the fluid. Separation here causes low pressure zones. Okay, and due to that there is an instability, and this type of adding flows take place. These are called vortices. So this vortex develop, and when this vortex is developing and breaking, okay, it causes a force in lateral direction. And unfortunately these are occurring at a particular frequency. That frequency depends upon the size, roughness, characteristics of the chimney and the speed of the wind. And every time when it is setting this side, it will cause a force in this direction. When it is occurring here, it will cause a force in this direction. And this becomes a harmonic force. What can happen in case of harmonic force? Its frequency many times matches with the lateral frequency of vibration of chimney. So it is not the longitudinal force which is a big problem. Okay, longitudinal force is more or less static. Okay, you can design a chimney for that, but this vibratory motion in the transverse direction across the floor due to vortex shading, this is a big problem, and all flexible structures have this problem. Okay, our cable stayed bridges also have this problem. Okay, so there if wind is blowing in this direction, the vertical motion will start, and due to that vertical motion the bridge may fall. So in case of flexible structures, and chimneys are one of the flexible structures, their normal wind load calculation which you do in case of buildings is not adequate. Okay, you have to take into account this phenomena of vortex shape, and then of course earthquake which we are studying. But as I told you, more than earthquake, it is problem of wind in case of chimneys. So if you are interested, I am not covering here. If time was there, in some earlier years I have covered wind design also. So you should learn the wind design as well, because you will never design structures for earthquake alone. Okay, you have to design structures for all types of forces. So learning only earthquake resistant design is not enough. Most of the cases, if you learn earthquake resistant design, all forces, other forces you can do very easily, because in building it becomes very easy to consider other forces. There is nothing much. Earthquake is the main issue. You learn earthquake resistant design, rest of this is get covered, but not here. Here wind, and that too dynamic behavior of wind, that becomes a problem, and here fluid dynamics comes into picture. Okay, so this needs more reading. IS 875 sorry, part 3 deals with that. So look in IS 875 part 3. Okay, especially how the vortex shading part is considered in design. Sometimes what we do, we provide what we call aerodynamic, because this aerodynamics, that becomes the big problem. So aerodynamic stabilizing. Okay, so what it does, it modifies. Problem is when this vortex shading is matching with the frequency of your chimney. So to avoid that, what you have to do, either you have to change the stiffness of the chimney so that the period changes, or you change the frequency of this vortex shading. Somehow disturb this vortex shading. So if this vortex shading, this aerodynamic stabilizer modifies vortex shading. You have to just provide this simple roughness, some disturbing element, due to which this laminar flow gets disturbed, and you provide it asymmetrically. So what will happen? That harmonic motion and the frequency of this will get disturbed, and once this gets disturbed, it doesn't match with the, as such this force is not very large. Larger force is in the longitudinal direction only, okay, due to drag. This force is not that large, but because of its harmonic nature and frequency matching with the chimney, it gets on, the response gets on accumulated. So in every cycle, resonance happens. So resonance is the problem. So you need not to reduce the force, that is not the big issue. The issue is frequency. Somehow modify its frequency. So some simple devices like this, those can also change the aerodynamic character and the frequency gets modified, or the vortex shading here, you generating roughness here, it will convert the flow from laminar to turbulent. So some turbulence you have to create so that here the gap is not there and the vortex shading is not taking place. So if you can achieve that, then this problem can be solved. So these simple devices can also do that. When we are talking about tall buildings, there also this problem is there. So they are just changing the shape of the corners sometimes. Change the shape of the corners or provide some rough element at the corners. It can do miracles. It can change the wind forces drastically.
Sir,
Yes.
since this is the symmetric structure about one direction, when wind is going to that, so when it is changing direction from this to this and from this to this side, the force generated from this side and this side should be equal as it is changing. So it will cancel out.
If it is happening symmetrically, what happens in the vortex setting? Instability occurs. And when instability occurs, the forces in both the directions are not same. At one instant it is in this direction, and another instant it is in this direction. That's the phenomenon of vortex setting. In instability, if everything was going on symmetric, then there was no problem. Okay. But asymmetry arises here because of this. Both these eddies are not forming together. One eddy forms, then eddy forms on the other eddy current. So if these eddy currents were forming symmetrically, then what you are saying is correct. Then there will not be any net resultant force. But when eddy current is forming from the left side, it is not forming at the same instant at the right side. It will occur at a different interval. Then left, then right. So this type of phenomena happens. And due to that, we get this type of motion, vibratory motion in the transverse direction.
And second thing that you are saying that we have to make the rough surface here. When we create the rough surface, there will again be one problem will be there. Like that, if you consider this as a ball, it will try to move this direction at the rough surface and another rough surface. There will be large friction on this side, and there is also large friction on this side. But due to this unbalance of this force, this chimney will try to twist, and due to that twisting, like on one side there will be addition of force and another side decrease in the force. So that will again generate unbalanced force on there.
So in this direction, I told you that the force is more or less static. In longitudinal direction, the force is static. Problem was in the transverse direction. So these are not very large elements, small elements only, which just disturb the flow of air. When the flow of air is disturbed, then turbulence will occur. And when turbulence occurs, then this area behind this is no more a shadow jet. Here also wind will come. And then this eddy current formation will not take place. Okay. Regarding asymmetry, okay, so that you can take into account. Whatever force you are getting, because these devices when we are putting, we are performing their test in, you can't analytically solve it. We are performing their test in wind tunnel and whatever forces we are getting, longitudinal or torsional, we will design. So designing for static forces is easier because forces are not that large that we cannot design. Okay. Problem is this harmonic motion, because the harmonic motion goes on building up. Okay. So the problem of harmonic motion is there in other cases also. So I give one example. Suppose there is a bridge. You might have learned in your high school that when army is moving on the bridge, they do not march. They break the march past. Right? Some of the people claim that the Morbi bridge, which collapsed, that happened because people were trying to shake it. Okay. So if you are causing vibrations with the frequency of the bridge, okay, the response will go on building. Okay. So suppose you have a very small motor. You know, eccentric mass can generate a harmonic motion. So if you create an eccentric mass and rotate it, you will get a vertical force which is very harmonic. You have learned in theory about it. Suppose I take a small motor, okay, put it on the bridge. Nowadays you might not have seen, but earlier days when these tape recorders were there, inside the tape recorder, there used to be a small motor. I take that small motor, which can run with a single 1.5 volt battery. Okay. Motor can run small eccentric mass. I change its speed so that frequency is matching with the bridge. I put it on the bridge. Bridge will start vibrating. Can I cause failure of the bridge? Can it be used as a bomb to destroy a bridge? A small motor with just one cell, you don't need any TNT or anything, you can destroy just with this small motor. Can you do that? Think about it and tell me on Monday. Okay? So, we will be dealing here with earthquake forces. If you want to learn chimney design, look into, or whenever you will need in future, even if you are not learning now, future maybe some of you end up designing some chimneys, then you have to keep this in mind and you have to look for IS 875 part 3. So there, this vortex shading effect is given. How to calculate that? Okay. So seismic design in seismic design, first of all, you have to obtain the period of vibration. So, a chimney, this may be treated as a cantilever. You know how to calculate a period of vibration? Solving the continuous system. What you learned in your theory of vibration, vibrations of continuous media, okay, continuous system, where the mass is distributed, and you have done the solution for simply supported beam and cantilever. So equation for cantilever beam you can use. Alternatively, you may use Rayleigh's method. You have done Rayleigh's method. So what is Rayleigh's method? If you know mode share, can you calculate frequency? What we call Rayleigh's quotient. What is Rayleigh's quotient? This omega square, which is phi transpose A phi over phi transpose M phi. This phi is n into 1, k is n into n, phi transpose will be 1 into n. So what will be this numerator? 1 into 1. That means a scalar quantity. This we call modal stiffness k star. Similarly, this will also be 1 into 1. This we call modal mass m star. Okay. If you have approximate mode shape, in place of this phi is the accurate mode shape, even if you have approximate mode shape, let us say psi, you can use the same method. And it has been observed that the error in frequency is much less than the error in psi, the mode shape. So even if you have got an approximate mode shape, you can predict quite accurate frequency using Rayleigh's quotient. And one of the close guess of this psi is deformed shape of the structure under its own load, okay, in the lateral direction. Own weight acting in the lateral direction means the chimney, if you tilt it 90 degree. So whatever will be the deflected shape, that will be your psi 1, psi 2, psi 3, psi 4, psi n. With the psi vector, you can write down as psi 1, psi 2, psi 3, so on up to psi n. This is nothing but the deflected shape of the structure. This is valid for buildings also. Okay, you can get a very good estimate of the mode shape from the deflected shape under cell weight applied volume. Okay, so we can make use of this. Now, it is a continuous system actually, but what we can do is we can lump mass model. So in lump mass model, this chimney weight, chimney mass, we will lump at certain point and the minimum 10 points should be there. So let us say all these masses are lumped at the uniform distance. So this will be m by 2, and m is the total mass divided by m, and then the force will be mg. Do you agree? The total mass for m, we have divided it into n points. We have distributed it at n points. Each point will have n mass and mg force, and the topmost point, because this will have mass lump from this to this. Here it will be only half to 2 degree. Okay? So that's why we are considering. Can you calculate the deformation here? Delta 1, delta 2, delta 3, etc. Or psi 1, psi 2, psi 3, etc. Let us say, let me call it delta 1. Delta 2, delta L. Can you find out? Any method you know by which manually you can find it? You can always make a model of this, a computer model of this, and find out this. But manually, any method you know, you have done.
Yes, we can think.
Yeah, I want budget method, not your bill.
I will
Which
outline.
method?
We will outline like this. For this deflection, I will put consumption zero.
Right.
And this part as a again to down.
So how to calculate the displacement? Which
Same.
method you will use?
We will calculate theta here, deflection here.
Right.
Then this deflection, first this deflection,
Uh-huh.
theta here, then this equal to this deflection.
Right.
Theta into
How you will calculate this deflection and displacement here? That's what I want to know.
that is formula of PL.
Which is formula?
For concentrated flow, PL to upon
Will not work here. That is for single load. If single load is acting, here single load is not acting. All the loads will cause effect of all these loads will be here also. So this displacement will not be just because of this load. All loads. So PLQ over 3I will not work here. So how you are going to
we
do
will get general moment equation.
general moment equation?
Mx in the form of dx.
Good.
Then d2 by dx we are equal to mx. We will put the boundary limitation, we will solve that constants, and for any value of x we will calculate that one.
Okay. So you can treat this as UDL also. Okay. And that then at any distance x from here, what is our moment?
W into x into x y.
Hmm?
W into x into x y.
So Ws square by 2. Okay. And you can write down the equation E as d square y by dx square is equal to mx. What are the boundary conditions?
Theta at
D, first of all, y at x equal to L is equal to 0,
and theta also.
and dy by dx at x equal to L. You can solve this, then you can get at any point. You can calculate a different point. This is one of the methods where you are solving the differential. You know any other method? Moment equation. That is, I told you geometric method of solving the same equation. So same equation you can obtain geometrically also using moment equation. Okay. In moment equation theorem, what you have to do? First, draw the bending moment diagram. The bending moment diagram here, how it will look like? Actually, because of UDL, it is parabolic, as you have seen. But we have divided this into different points. So how the bending moment diagram will look like? The bending moment diagram will be actually piecewise linear, like between different points, it will be linear. you can get these values here easily. Take this trapezoid, the displacement here will be what? Moment of this about this point. Then you can take this another trapezoid here. Then take moment about this of this trapezoid as well as this trapezoid. You can make a tabular calculation and you can calculate the displacements here. Okay, and then you can calculate T as 2 pi square root one by G gamma. And what is gamma? Wi or Mi delta I divided by you can see that this formula is same as we have done in direct displacement design for delta D. Okay, so this is inverse of this is actually delta D. So this is 2 pi square root delta by G. And I have already given you the derivation of T is equal to 2 pi square root delta by G. Okay. So delta of single degree freedom system, that is inverse of mode participation factor. Okay. The code gives an alternative method also for obtaining period, and that is T equal to Ct square root of W T into H over Es A. So Wt is the total weight of the structure including weight of lining. That's why this T subscript is given. Wt is total weight including lining. Because lining mass is also supported by the structure. So that also needs to be considered. H, height of chimney above base. Es, modulus of elasticity of the material of structural shell or outer shell. The shell which is resisting the load. Okay, I told you that there can be an inner shell, there can be an outer shell. Outer shell is resisting the load. So that matter. It may be made of concrete, it may be made of steel or assembly. So that value of E. Okay. Area of cross section of structural shell at the base. So mass will be considered of both the shells, but area will be area and E will be considered only of the structural shell. And G, of course, no acceleration due to gravity. And this coefficient Ct This is given by code. So if you have the copy of the code, you can have it. Look. Okay, so on page 17 you have table 7. Are you able to look at it? Then please note that this code came in 2015, but after that two corrections are come in 2017 and 2018. So in that correction, one of the corrections, this damping clause has been changed. So amendment 1, the damping clause changed. Read at the damping clause here in the code. What does it say? It says 5% for steel, 5% for concrete, and 7% for brick masonry. But the modification has given in table. It has given different damping in BE and MC. I don't know what they will do with the damping at MC, but they have given. Okay. And for steel it is 2%, reinforced concrete 5% at BE, and brick masonry 7% at BE. So I don't know whether this amendment A1 and A2 must have been given to you when we are able to look at this amendment or you don't forget the amendment. So damping has been changed in those amendments.
So how damping will change at different level of which is the given by structure?
Can anybody answer this? Why different levels of damping at different levels of earthquake? Why should damping depend on level of earthquake? This is not historic. That is taken care of by R. Damping depends on omega frequency. Damping depends in some of the materials on frequency also. For example, in soil, it depends on frequency, but not in steel and cotton. So it is not depending on frequency. Frequency will remain same. Damping depends on amplitude. Okay, even material damping. If the structure is vibrating with small amplitude, the damping will be less. Even in an elastic range. I am not talking of hysteretic damping. Elastic range also, the damping depends on amplitude. Larger the amplitude, more will be the damping. Okay, because larger the amplitude, more strains will develop. Cracking may be there. Okay, there will be more movement at the joints. So energy dissipation will be more when the amplitude of motion is more. Amplitude of vibration of the structure is larger. Naturally, in case of MC, the vibration will be larger. If you look the book by Yogendra, he has a chapter on damping, and there he has explained that at different strain levels, up to epsilon y, up to yield strain also, at different level of strain, how the damping changes. Okay, maximum damping we will get when our amplitude is epsilon y or larger than epsilon y. Larger than epsilon y, then also there are two components. One is the hysteretic and another one is the material. So we are talking about material damping only, not the hysteretic damping. That is taken care of separately. Now hysteretic damping, you consider it response reduction factor. R, once the period is known, you can calculate H. So that will be Z by 2 into I by R into SA by G at this T which we have calculated into beta phi. Beta xi, how we will calculate? In the same code, yesterday in case of tanks also, I referred to this code for calculation of beta. Actually, in this code only, the table is given. If you look at answer A on page 20, here the multiplication factors for different dampings are given. You can compare it with the formula of Euro code which I have given in DDBD. 0.1 over 0.05 plus xi whole to the power 0.5. So you can compare with that formula, it is close. You will get close, but there may be difference. And that formula is not valid for less than 0.5%. That also, that Euro code formula, that is only for damping higher than 5%. For lower than 5%, it is different. So this table gives you the complete range from 0 damping to 30%. Okay, so you can calculate H like this. Then the task is to calculate the bending moment variation and the shear force variation. Yes, this is variation of V and this is variation of moment. So at any distance x from the top, okay, the the shear force is given as CV into AH, WT, the total weight, into dV. Similarly, M is equal to CM. No CM. It is equal to AH, WT into H bar. What is this H bar? H bar is the height of CG of mass. Okay. This CV, dV and dm, these are given in the code, the table. So CV is given in the same table where we have seen CT. Same table gives you coefficient CV, and dV and dm are given in table 11. And you can see the value of this CV is increasing. So the distance is given from the top, and at the bottom it is 1 g. Okay, so this is 1.2. Similarly, you have CM. This is also increasing, and at the base, this value is 1.2. So it gives the shape of the shear force diagram and the bending moment diagram. That's all.
It is H or H bar.
Sorry.
That is H bar or H?
H bar.
Then sir, it should not be the CG of the mass. It should be the centroid of the load distribution diagram.
That is taken into account by dm. CV coefficient, right? There is no CM coefficient. That's why I have also written CM and then I delete. There is dm. So moment is simply AH into WT into at the base. dm is equal to 1. So the moment at the base is simply AH into WT into HY. So this AH, they are assuming to be acting at the CG of the mass. In figure, oh sorry, I have written CV and CM. Actually these are DV and U. Okay?
Why the CV and DV are applied?
Why?
This CV and DV are coming.
Suppose you want to calculate the bending moment here, because the size of the chimney may go on changing, so it should be safe not only at the base, it should be safe at all the sections. So you need bending moment at different sections.
Yes.
So you need the variation of the bending moment. So this is giving you the variation of the bending moment, or in other words, shape of the bending moment diagram. So this dV and dm are giving you the shape of the shear force diagram and shape of the bending moment, so that you can calculate bending moment and shear force at any section. Okay? So this completes our course. You can do tutorial 7 now, and we will be meeting